get ready for presentation. I want to get ready for the presentation, and I have to present this paper. Mamba linear time sequence modeling with selective state space. I have no idea what it is. An ideogram. So ideogram, I think, is something you can use to create slides. Okay, it seems it creates photos. Let me see. Screen share. This is. What will you create? Describe. So it's just boobs. Girls with boobs. That's it. At the end, it's all about it. Cat and girl. This one is just the face. So I heard I can give it a. What is this? Who is this? Captivating Picasso-nier realistic painting featuring 90 rockabilly inspired family. All right. So design, generate, general, editor. I don't see it. Let's see if ChatGPT does it for us. Create slide for presenting this paper. That's actually really good. I can present the same shit. Here's a suggested outline for the presenter. Can you create a slide? I have to go. Okay, ChatGPT also created. This is it. I was not present here. It created for me. This is the future, by the way. I mean, the way you want to work. You want to be not present where you work. You want to make money while you are not there. And I already started it. Please read Rich Dad Poor Dad. Again, you know what? I'm not gonna advise you. I'm gonna advise myself, and I want to tell myself that go read it again, because I want to do that more and more. cut, paste. So Mamba linear time sequence modeling with selective state space. Key innovations and results. Introduction. Transformers dominate but suffer from quadratic scaling inefficiencies. Need for models that scale linearly for long sequences. Mamba, a selective state space model system offering efficiency and scalability. Key innovations. Selective state space model enable input independent content based reasoning, hardware aware algorithm, efficient GPU utilization, 3x speed up over prior methods, simplified architecture, combines selective state space combines this state space model and convolution benefits, omitting attention layers. Oh, so it removes attention layers. Performance highlights, language modeling matches transformers. Really good. Before reading a paper, just getting an idea of what it is in 7 slides. Perfect. Language modeling matches transformers twice its size. Wow. 5x inference throughput. Audio and genomics outperforms. Okay, what is throughput? I don't know what throughput is. Language modeling matches transformers twice its size, 5x inference throughput. Audio and genomics outperforms state-of-the-art models in tasks requiring long text, 1 million tokens, synthetic tasks, perfect generalization in tasks that like selective copying and induction heads. What is this head? Oh, head was input, attention. Another Mumbai slide. Same stuff. Alright, what's wrong with that? Audio and genomics outperform state-of-the-art models in tasks requiring long text, synthetic tasks, perfect generalization in tasks like selective copying and induction heads. Oh, okay. Throughput. Where was throughput? Efficiency. I didn't find the throughput. Okay. What is a throughput? What is inference throughput and throughput in general? Alright, how do you pronounce throughput? Throughput. 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 The amount of material or items passing through a system or process. Throughput, like input. Fast data throughput. Alright, so Throughput in general refers to the amount of work or data a system can process in a given amount of, like 10 multiplication per hour. It's a key performance metric in many domains and can mean different things depending on the context. Networking, the rate of successful data transfer over a communication channel, bits per second. Manufacturing, number of products produced per unit of time. Compute throughput. Throughput? No. Troubleshoot. That's something else. The number of products, video shoot. Throughput. Alright. Number of products produced per unit of time. Computing systems, number of multiplication, exactly. Inference throughput. In the context of machine learning and AI model, inference throughput refers to the number of prediction of inference a model can generate per second during deployment. Okay, it's a critical metric when evaluating the performance of a model for real-time or production scene. Yeah. So what is the throughput of ChatGPT? Key factors: model architecture. Simpler architectures often achieve higher throughputs. Hardware, faster GPUs or TPUs. What is TPU? Increased throughput. Batch size, processing multiple inputs at once improves throughputs, although this is constrained by hardware memory. Optimization techniques like quantization or pruning can increase throughput. Inference, number of inference over time. Importance of inference throughput, real-time application, autonomous driving, conversational agent, high throughput, ensuring time. Actually, we can use these GPTs for like Waymo cars, right? Streets are the same. Scalability, higher throughput. Well, hopefully they should not learn from the accidents. Scalability, higher throughput means the system can handle more simultaneous users or large database. Cost efficiency, higher throughput on a given hardware setup reduces cost per inference. So what is Chat GPT's throughput? Has not been publicly disclosed in detail, but estimates based on similar suggest throughputs ranges: single query throughput, few queries per second for smaller workload, batch processing throughput, dozens or even hundreds of queries per second. Okay, so we got what throughput is. Who cares? Audio and genomic outperforms state-of-the-art models. So it is just using a state space model or like control stuff, dynamic and stuff. The art models in tasks requiring long context, synthetic tasks. What is synthetic task? Perfect generalization in tasks like selective copying and induction heads. What does this mean? What does the statement synthetic task perfect generalization in tasks like in the paper means that the model like Mamba performs flawlessly on carefully designed benchmark tasks that test the specific capability. The test. And it can generate generalized its solutions beyond crazy, the scenarios it was explicitly trained on. Synthetic task experiment. Okay, I don't have breath to read all of it. So synthetic task is the official benchmark that they create, and they wanna see how good a machine learning algorithm works. Memory, attention, or reasoning. Mongo successfully identifies and copies the relevant tokens, ignoring irrelevant ones, and generalizes this ability to sequences much longer than those seen during training. Induction heads task. Heads is about the attention, right? This task requires associative recall. For example, if the model encounters a pair like Harry Potter early in a sequence and later sees Harry again, it must recall and predict Potter. Challenge. This task tests a model ability to recognize patterns and recall relevant association in context. Mamba's achievement. Mamba solves the task perfectly, even for sequences that are order of magnitude longer than those it was trained on. Oh, that's great. Perfect generalization means that the model not only solves this task correctly on the data it was trained on, but also on the data benchmark. Extrapolates this understanding to new unseen data. Test it. For instance, Mamba was trained on a sequence of a certain length, but demonstrated success in tasks with sequences much longer than those in the training set, showing its ability to generalize its learned pattern to new contexts. This capability is significant because it reflects robustness and versatility traits that are crucial for practical deployment in real-world scenarios involving unseen or variable data, of course. So synthetic tasks and a synthetic benchmark, how they perfect generalization. Implications: efficiency, linear scaling, high throughput, minimal memory overhead, versatility, applicable across multiple domains, including language, audio, and genomics. Open source, model code, and pre-trained checkpoints available. That's amazing. Yes, you need to. Oh, what is TPU, by the way? We found a GPU. What is TPU? CPU is computing processing unit. GPU is graphic processing unit. TPU is tensor processing unit. Okay, TPUs are made by Google, by the way. Oh, so is Mamba from Google? No, Mamba is not. Okay. Carnegie Mellon University and Princeton. Alright. Clear improvement in quality across domains. Conclusion: Mamba is the first linear time model to rival transformers. Okay, it is LTI, linear time, in multiple domains. So transformers used to do quadratic time. Mamba is doing it in linear time, and so it's far better. Why not everybody knows? And what else? They are using a state space model. That's the way to do it instead of what? Combines efficient attention mechanisms. Yeah, instead of attention, combine efficiency with the state-of-the-art performance potential for broader applications in sequence modeling. Alright, Mamba is this. Let's go inside the paper now. Foundation models now powering most of the exciting foundation models. What is foundation models? Now powering most of the exciting applications in deep learning are almost universally based on transformer architecture and its core attention module. Many subquadratic time architectures such as linear attention, gated convolution, and recurrent models and structured space states. That's a trap for any Persian guy. Structured state space models. A structured state space. Am I correct? Structure, state space models have been developed. Why didn't we Persians say structure, state? Oh yeah, it doesn't make sense. Space models and have been developed to address transformers computational inefficiency on long sequences. Oh, so transformers have problem on long sequences, and these state space models came to do that, but they have not performed as well as attention on important modalities such as language. We identified that a key weakness of such model is their inability to perform content-based reasoning and make several improvements. First, simply letting the SSM parameter, what is SSM parameter? Be function of the input addresses the weakness with discrete modalities, allowing the model to selectively propagate or forget information along the sequence length dimension depending on the current token. Second, even though this change prevents the use of efficient convolutions, we design a hardware-aware parallel algorithm. In recurrent model, we integrate these selective SSMs into a simplified end-to-end neural network architecture without attention or even MLP blocks. MLP is Mamba. What is MLP block? What is MLP block? Multi-layer perceptron block is a fundamental building block in neural network architecture. Deep learning, it consists of one of fully connected layers, nonlinear activation function, something. So these are those Andrew NG was plotting them. And dropout layers. Blocks are used to process input data while applying learned transformers. Input vector, weight matrix, X is input vector, weight matrix, W, B is bias vector, Y is output, so affine function, activation function, like ReLU, rectified linear unit, the sigmoids, and normalization, version dropout option. overfitting by randomly setting some neurons output to zero during training. Modern order. So we have a very simple, right? Combination of, we have an affine function, sigmoid on it, then we do another affine function on this, and then we do another feed forward network which processes a multi-layer perceptron. Consists of two fully connected layers with a nonlinear activation. Between them, examples. These are often using vision models as part of the feature aggregates. So Mamba uses MLP blocks to provide nonlinear transformations and gating mechanism with its selective state space. Key benefits of MLP blocks: feature transformation, more useful for the task, nonlinearity, scalability. Now I want to look at an MLP block. Exactly. Perfect. Mamba enjoys fast inference, 5x higher throughput than transformer, and linear scaling in sequence lengths, and its performance improves on real data up to million length sequence. As a general sequence, the model backbone Mamba achieves the state of the art. So it has a lot of benefits that I can just mention in my presentation. These are the things Mamba does. Several modalities such as language, audio, and genomics on language modeling, our Mamba 3B model outperforms transformers of the same size and matches transformers twice its size, both in pre-training and downstream. So, one slide is just one slide, I want to say one Mamba's achievement and comparison to achievements in comparison to transformers. Okay, one is Mamba's achievement, the other one comparison of Mamba to transformers. I mean, they are kind of overlap. Comparison. So this part, I want to take 30 minutes of my presentation to transformers. Alright. I mean, abstract says a lot, by the way. I don't care. Introduction, foundation models, or large model pressure in the massive. Foundation model. FM is frequency module. Modulation. Foundation model of a sequence model operating on arbitrary sequence. And genomics. Well, this concept is agnostic to a particular choice of model architecture. Modern FM are predominantly based on a single type of sequence model, transformer, and its core attention layer. The efficacy of self-attention is attributed to its ability to route information densely within a context window of complex. Property brings fundamental drawbacks. Drawbacks of and an ability to model anything outside of a finite window and quadratic scaling with respect to the window length. An enormous body of research has adapted to a more efficient variance of attention to overcome these drawbacks. Tehrani, alright. I love it. A lot of Iranians are in all of these papers, but often at the expense of the very properties that makes it effective. As of yet, none of these variants have been shown to be empirically. So, good job for Tehrani, shown to be empirically effective at the scale across domains. Alright, so shortcomings of transformers. Shortcoming of transformers. Recently structured state space sequence models. So, state space sequence structured state space sequence models have emerged as a promising class of architecture for sequence modeling. These models are interpreted as a combination of recurrent neural networks and convolutional neural networks. So it is a combination of recurrent neural networks and convolutional neural networks, which I don't know both of them. Inspiration from classical state space model, and which is inspired by Kalman filter. This is very interesting. SSM models. This class of models. This class of models can be computed very efficiently as either recurrence or convolution with linear or near linear scaling in sequence lengths. Additionally, so these are all the benefits they have these are the same thing we already had. Mechanism for modeling long-range dependencies in certain data modalities and have dominated benchmarks such as long-range arena, many flavors of SSM. This is a lot of works. Have been successful in domains involving continuous signal data such as audio and vision. However, they have been less effective at modeling discrete and information dense data such as text. Right. So SSMs are good for continuous, not good at discrete, especially text. But Mamba, it seems, is going promising. We propose a new class of selective state space model, SSSM, that improves on prior work on several axes to achieve the modeling power of transformers while scaling linearly in sequence lengths. So selection mechanism. First, we identify a key limitation of prior models. They believe to select data. So they cannot be efficient in selecting data in an input-dependent manner, focus or ignore particular inputs, building on intuition based on important synthetic tests such as selective copy and introduction heads. What is selective copy and introduction? We design. So that's the way they improve the SSM, by these synthetic tasks. We design a simple selection mechanism by parameterizing the SSM parameters based on the input. This allows the model to filter out irrelevant information and remember relevant information indefinitely. Hardware-aware algorithms. So let me choose this. What is selective copy and information head? Induction heads. What is selective copy and induction head in the paper. Induction head tests are synthetic benchmarks designed to evaluate and demonstrate of sequence modeling model. Test specific abilities such as content-based in memory retention and context-aware decision making. Here's a detailed explanation of each. Exactly. The test requires the model to copy specific tokens, data points from an input sequence based on while ignoring irrelevant tokens. The positions of the tokens to copy are not fixed but vary. And the positions of the tokens to copy are not fixed but vary, meaning the model must understand the content of the input to decide what to copy. Relevant timing or positional cues challenges. Many models like recurrent neural networks or convolutional models struggle, but it is the combination time-aware dynamic or fixed patterns which fail when the selection occurs on the input content. Significance, selective copying test. Okay, we work until 2 and after 2 I start to make my slides. Many models like recurrent which fail in selection rating. Significant selective copying test the models ability focus selectively on relevant tokens. Like I have a finger, like I have a ring. Alright, focus selectively on relevant tokens. Maybe it is some in primal behavior. On relevant tokens, filter out irrelevant data based on input dependent reasoning. Filter out irrelevant data based on input dependent reasoning. So Mamba does perfect. Its selective mechanism, ability to focus on specific tokens and generalize this behavior. Much longer sequence than seen during training. Induction head. What is induction head? Task description. The task involves associative recall. I don't know that. A core mechanism in many large language. Okay. For example, if the model encounters the pair Harry Potter earlier in the sequence, and it should associate and recall that Harry, again, it must Harry's family name is Potter. Challenge, the model must remember associations over long context. Understand patterns and recall them correctly when a partial sequence like Harry reappears. Okay. Significance, induction heads are a critical component in LLM. So these are new for me. I'm gonna talk about them today. Enabling, honestly, what I wanna present today is the summary of my chat with ChatGPT and the highlights I have are critical components in enabling them to perform in context learning, such as completing patterns or recalling facts based on prior occurrence in a sequence. Mamba's performance. Mamba excels in this task, solving it perfectly, even for sequences thousands of times. And I want to have this mindset that I'm bringing this information on the table and people are free to discuss it. Like we are other people who read the paper, specifically Mardovic, so he knows it and he can help me. I don't know something, no problem. So in this task, I just mentioned the things that I like about this paper. Excels in this task, solving it perfectly even for sequence thousands of times longer than those seen during training, showcasing content-aware reasoning, the ability to generalize associative recall across different lengths. Why this task matters, highlight model limitation, Tasks like this expose the weakness of traditional sequence models, lack of content awareness, or difficulty with long context. By the way, isn't it crazy that ChatGPT creates you PowerPoint? Does it create the PowerPoint on my computer, or it makes it there in OpenAI and sends it to me? Wow, this is fantastic. I mean, we are blessed. Highlight model limitations. Tasks like these expose the weakness of traditional sequence models, lack of content awareness, or difficult. Demonstrate model strengths. Mamba's ability to solve these tasks validates selective statement and generalization. Controlled experiments to evaluate fundamental sequence modeling capability. Demonstrate Mamba's superiority over the architecture in handling content based on long-run dependencies. Then we have hardware-aware algorithm. This simple change, a technical challenge for the computational of the model. In fact, all prior SSM models must be time and input invariant. Technical challenge for the computation of the model. In fact, all prior SSM models must be all prior ones, time and input invariant in order to be computationally efficient. We overcome this with a hardware-aware algorithm that computes a model recurrently with a scan instead of convolution. So it scans instead of convolution, but I don't know what it exactly means. But does not materialize the expansion I/O access, input-output access between different levels of the GPU memory hierarchy. I don't understand this, and I'm not that interested to know about it. The resulting implementation, I just want to mention, it is also hardware-aware algorithm. It is faster than previous methods, both in theory, scaling linearly in sequence lengths, compared to pseudo-linear for all convolution-based SSM, and on modern hardware, 3x faster on 800 GPUs. Also, we have architecture. It's fantastic. By the way, let's go, before going over every detail, I want to see what is paper made of. Let's go over the title. Alright, so after introduction we have state space models, and which is this, and there is a bit of math involved, like linear system control stuff, dynamical systems, and we have selective state space models, and improves the state space with selection, and then we efficiently implement it. We have another thing here. And then we have empirical evaluation. These are the just 10 first pages. And then they use it for DNA modeling. Interesting, DNA is crazy, right? And I mean, just the amount of knowledge we can create with these powerful tools. Dude, I think discussion. Oh, okay, it's just 16 pages. So what the conclusion at page 17? So what is the rest? I mean, it is 36 pages, but it finishes at page... God, how many reference? And then they have a discussion selection mechanism. So first of all, good news. It is much shorter than I thought. Then they are talking about the architecture of the system. Linear attention, long context method. it's like they're defining everything that they did. Mechanics of SSM, selective SSM, and they are going deeper in the appendix. Hardware algorithm, they're talking about it. I mean, these are fantastic. This is such a well written paper. Like when you write a theoretical paper and you leave the proofs um, in the end. Audio details. Efficiency benchmark. Wow, it's perfect. It's only 16 pages, so we can go much faster. So, we said, why is it good? We also did hardware aware algorithms. That's fantastic, how to read a paper. I'm really proud the way I read this paper. So let's go. So the algorithm is hardware aware and it improves it. Theory scaling linearly as compared to pseudo-linear modern hardware on 800 GPUs. What is 800 GPUs? It doesn't matter, to be honest. But we are doing asking it, what is control V? Okay, it's an NVIDIA 800. It's a high performance graphic processing unit. That's it. Alright. I'm not reliable for giving feedback on this. Architecture. We simplify prior deep sequence model architecture. So also our architecture matters. Architecture. We simplify by combining prior SSM architecture with the MLP blocks of transformers into a single block, leading to a simple and homogeneous architecture design. So that's the architecture. They have SSM and they have some MLP that creates Mamba, incorporating selective state space. So it is state space, but it's also selective. That makes it really good. Fully recurrent models with high quality. Selectivity brings strong performance on dense model. Genomics, fast training and inference, computation because of the state space. Training auto-regressively during inference requires only per step since it does not require cache of previous elements. Long context, the quality and revision. Empirically, they are validating Mambas, but they're FM backbone foundation model. Several types of model. By the way, yesterday, last time we were talking about RetNet, and RetNet was also something linear compared to transformers, which are quadratic, and I don't know why don't we start using them, or maybe we have already started. As being the large language model, solve them easily, but also extrapolate solution indefinitely long, greater than 1 million token. Audio and genomics, mobile performs prior sashimi. Hyena is the name of a model. Who loves that animal? Hyenas are disgusting, by the way. They deserve no love. They look very much like dogs and wolves, but they are disgusting. And of course, actually, I wanna watch a documentary on hyenas. They always show as the bad man in documentaries about lions and especially leopards. They are so mean to female leopards. And for me, female leopards are the most interesting animals in like Africa. Like lions are strong, but female leopards, they are screwed. They got the worst card, to be honest, and still they survive. They are so inspiring. Is it the word? They inspire you to be tough. Audio and genomics. There are a lot of documentaries, but I think the last one I watched was Living with Leopards on Netflix. Crazy. And I also watched another Mother Leopard, something like that. The similar story, and it was great. Audio and genomics. Mamba upper prime. Okay, we already did it in both settings. It's performance longer than X. Language modeling. Mamba is the first linear time sequence model that truly achieves transformer quality performance. What does Mamba mean, by the way? What does Mamba mean? What does Mamba mean? Mamba or Mamba? Linear. Oh, Mamba is a snake. Is a highly agile and fast snake. Alright. Mamba. Like pythons, cobras. So it's a snake, fast moving, highly venomous, snake of the genus Dendropiuthi in the family name. How fast they move. Linear scaling. Alright, oh no. Oh, because it is linear, they said it's a snake? Alright. So there was another model. It was called Hippo. Dude, really felt good. Okay, fully recurrent models that keep our highly language modeling. All right, what about language modeling? It's the first linear time sequence model that truly achieves transformers quality. That's amazing. In pre-training perplexity and downstream evaluation, scaling laws up to what is laws up to? 1 billion parameters. We show that Mamba exceeds the performance of a large range of very strong modern transformer training based on Llama, our Mamba language model at 5 generations or whatever. I don't know what to present about. I mean, scientifically, are they going to involve the algorithm or math? All right, stasis space model. Let's go. What is it? What is this? Well, we know what is it. It is the controller stuff, and we have some mathematics here, and so we have computation, we have discretization, we have linear time invariant, structure and dimension, general status space model, and then we have SSM architecture. RetNet is also one, linear attention, hyena, and that's it. I don't think it is very important here. Selective status space model. Maybe this graph is important. HT minus 1. Structure. Dude, motherfucker. Sometimes you say structured status space sequence. Sometimes you say selective status space sequence. Sometimes you drop the sequence. A recent class of sequence models for deep learning that are broadly related to RNN, CNN, and classical status space model. So they are mixing this neural network stuff with a status space. They are inspired by a particular continuous system. One that maps. What is one? Of the equations. Maps select with hardware-aware state expansion. So we have GPU HBM and we have GPU SRAM. HT minus 1 comes in, it goes to A, and these are the status space multiplication, goes to CT, goes to output, YT, XT comes in, project, selection mechanism. What is project? What does project? BT, and that's it. What is GPU SRAM and what is GPU HBM? What does GPU HBM in figure 1? Graphic processing unit, high bandwidth memory. Type of memory architecture used in GPU provide extremely fast data executive handling computation, such as deep learning, high performance computing, HPC's high bandwidth memory. Alright, I'm not gonna further detail. What is SRAM? What is SRAM? So RAM is static random access memory. So we have HBM, which is Harvard Business Management. What was it? High bandwidth memory, and SRAM is Static random access memory. Static random access memory. Overview. Structured SSM independently map each channel D equal 5. What is 5? There are 4 of them. Oh, there are 5. Of an input X to output Y through a higher dimensional latent state H n equal 4. Prior SSM avoid materializing this large effective state to byte size B and sequence lengths. Clever alternate computation path requiring time invariant. The delta, what is delta? Oh, so the project does the selection mechanism. Materializing this larger, what is dn? Through clever alternate computation path regarding time variant, the delta ABC parameters are constant across time. Oh, so delta ABC are constant, but it is delta T. Our selection mechanism adds back input independent dynamics, which also requires a careful hardware to only materialize the expanded. So it is not an algorithm that you can do, you cannot scale in the sense that it is independent of the input hardware. Hardware is more efficient levels of the GPU memory hierarchy. Where is the delta showing up? The first stage transforms the continuous parameters delta A and B to discrete. But delta is not shown in these formulations. To discrete parameters A bar and B bar through fixed formulas. Oh, okay. This delta A bar is FA of delta and A, B bar is FB of delta and A, where the pair of FA and BA. It's called discretization rule. Various rules can be used, such as the zero order hold defined in equation 4. EXP of delta A, and B bar is delta A inverse, EXP delta A. Alright, first step of the computation, graphing the computation of the two-way linear recurrence or global computation. Recurrent mode for efficient regressive inference. This is also so the model switches. That was something that happened on RedNet as well. I like linear time invariant. An important property of equation 1 to 3 is that the model dynamics are constant. Okay. Let me see, what was the word I wanted to... Oh, what is the project block in figure 1? What was the project block in figure 1 does do? The process of transforming input sequence into a higher dimension latent space. Okay, so it's an embedding. For further processing by selective states this enable about the gradient input data for the project block. The project will serve as the input transformation layer, perform the function dimension it maps the input signal into a higher dimension space or latent states H for sub. If the input has a dimension D, the projection may map it in lattice as the n greater the capacity of complex representation. Rating and enable selectivity. How does this cause enabling the high dimension latency facilitates the selective state display well to dynamically focus on relevant portion of the inputs. How it works. Learnable weight matrix and bias to higher dimension and pass to SSM layers. Is it also on the photo? So H comes inside. Oh, this is another H, by the way, or it is X of E. I see. So H is the input and CHD, where is it? I see. Significance of data preparation, enhanced represent. All right. So LTI is connected to recurrence and convolution. So recurrence or convolution or LTI. So there is no non-linearity. That's stupid. There should be some non-linearity. There should. So, however, a core insight of this work is that LTI models have fundamental limitations in modeling certain types of data, and our technical contribution involves removing the LTI constraint while overcoming the efficiency bottleneck. All right. How do they do it? How do they remove LTI constraint? Selection mechanism. By the selection mechanism we do that. So it is time variant. It's linear by time variant. What would you want? Input dependent. So they make this data space one. Right, gets back to paper. Structure and dimensions. What do we know? Or so named here. So they need to have some structure, like the hexagon. Is this when I can all be represented by n numbers to operate over? They use D for the number of channels and also a matrix. Where is OBLDN? What is B also? B is the batch size. I wanna do a presentation like a podcast. I will take my chat GPT with me and we talk there. Who cares? I don't think I need that. I hate first of all, I hate presentation. Also, I hate classical presentation. There is too much pressure on the person. Like giving Oscar awards, general status-based models. Throughout this entire paper, we use the term SSM to refer exclusively to class of structured SSM or S4 models. What is a S4 model? I have no idea. Somebody can help, probably. And we will play along. I use these terms in there. We also include derivatives, models, etc. SSM architecture that can be incorporated into end-to-end neural network architecture. I'm actually kind of like, you want to talk about this paper and share our thoughts? And I'm hosting. I'm the moderator using ChatGPT. That's it. Standalone that can be. That's my job. And that's too much actually. That into end-to-end neural network. We also sometimes call SSM. Standalone sequence transformation. End-to-end neural network architectures. So called SSM architecture, SSS and SD, which are also seen in neural linear convolution, which will also have linear attention. Alright, so there are other state models that they want to talk about. S4. Hyena. RedNet. RWKV, recent RNN design for language modeling. Linear attention approximate. Other closely related SSMs and architectures are discussed further in an extended related work. Okay, S5. So these are big systems. Honestly, it's not my thing. I mean, I like that I'm presenting something that's not my thing. I have less expectation. Okay, now what is the selective status space? What was the previous one? That was the status space models, now we have selective ones. Oof, I'm tired. So maybe this is the part that is the most important. Yeah, I think that is the most important part. And they have like some results on evaluation on DNA and different stuff, and discussion and conclusion. Yeah, so okay, we entered the most important section of the paper. That's it. That was so easy to read. So that the stainless space models was kind of a prerequisite to know. I really want to go get some cocoa milk before starting this section. Something inside me says no. Alright, so I take a walk. So the first section, what was the first section saying? These are the benefits, why it's working. Transformers are not working. Motherfucker, I'm using ChatGPT and it works. Then the other thing, state space model, which had almost nothing, and it said okay, it's working linearly, and gave some structure. And sequence and state and space and model. And now we have the selectivity, which removes the LTI from it. So selective. Oh, it's about selective copying and the induction heads. Those are the two tasks that they are doing synthetically to make it work fine and have like long memory or something. Okay, so already we got something about it in the introduction. Let's dive into it. We motivate our selection mechanism using intuition from synthetic tasks. Then explain how to incorporate this mechanism into state space models. Mechanism using intuition. So it is a time varying. The goal was to make it LTV instead of LTI. Cannot use convolutions presenting. Bike LTI can do convolution. LTV cannot do convolution. Technical challenge of how to compute them efficiently. We overcome this with a hardware-aware algorithm that exploits the memory hierarchy on modern hardware. We then describe a simple system architecture without attention or even MLP. It doesn't even need MLP blocks. Finally, we discuss an additional selection mechanism. Wow, this is crazy. Okay, it said it all. Actually, I can just copy paste this for my slide. This is crazy. Really liked it. Innovation selection as means of compression. It's compressing context into a smaller state. So this is where the idea comes. We want to compress the context into a smaller state. Sequence models from this so attention mechanisms do not compress context at all. What is autoregressive inference? I mean, I know what inference is, but what is auto? Autoregressive inference. It is a process in machine learning and deep learning where predictions are made sequentially. Each prediction depending on the output of previous step. So we are predicting based on our previous prediction. It is called mental masturbation. The method is commonly used in models for sequence data. Do you remember the famous talk? Such as language modeling and time search prediction, care, autoregressive, inference, the first word and so on. So every time, that's actually very beautiful about autoregressive. It doesn't say I want to predict the whole sentence. It says I just want to predict one. It's a one step at a time strategy. I want to predict the next word. Now I have a new text, and based on the new text, I want to predict the next word. And I like it. It doesn't think ahead too much. Like ChatGPT is not a person who is strategizing to talk to us. It's just talk to us normally. You know, I think about the next word and I share it with you. He's a nice person. He doesn't hide what he's thinking. Exactly. Natural or sequential tags because high accuracy disadvantages: slow generation, error accumulation, inability to parallelize. Oh, that's terrible. All right. So selection is compression, and compression is selection. Effective and inefficient. How can something be effective and inefficient? Ineffective. Efficacy and what does efficacy and effectiveness? The ability to produce a desired or intended result. Efficacy versus efficiency. Efficacy is the ability to produce a desired effect, while efficiency is the ratio of useful results to the effort put into it. So it is, what is it? Um, it is inefficient, but attention is really good. The result is good, but it is very time consuming or something. It's slow. Does not in efficacy and efficiency. Is efficacy versus efficiency same as quality versus quantity? Sounds like that. At all time, both effective and efficient. This can be seen from the fact that autoregressive inference requires. So, autoregressive inference is slow, so it is inefficient, but it is efficient. Efficient. What is efficient? We say efficient. Okay, there is no definition. Okay. Oh, efficacy is the power to produce an effect. Oh no. So wait a second. Efficacy. Adjective form. Efficacious. Efficacious. Efficacious.
Efficacious. Efficacious.
Efficacious. Successful words are. All right. Sounds like it. Effective and efficacious. Smaller state. Where is it? Explain does not compress context at all. For example, attention is. So why does it say effective instead of efficacious? What is the inefficient? You cannot be effective and fuck you. Efficacious versus effective. Efficient. Oh. Yeah, okay. Efficacy refers to how well something. Oh, efficacy refers to how well something performs under ideal circumstances, while effectiveness refers how well it performs in real world conditions. In a controlled setting is efficacy. Effectiveness is in the real world. Fuck. And efficiency is something else. Efficiency, effectiveness, efficacy. Does not compress context all. This can be seen from the fact that autoregressive inference requires explicitly sorting the entire context. So it cannot storing the context. It does not compress it, which directly causes the slow linear time over quadratic time training of transformers. On the other hand, recurrent models are efficient because they have a finite state, constant time inference, and linear time varying. However, their effectiveness is limited by how well this state has compressed the context. So based on this principle, we focus on two running examples of synthetic tasks. Selective copying modifies the popular copying task by varying, what is it that modifies the popular copying task? Varying the position of the token to memorize, it requires content-aware reasoning to be able to memorize the relevant colored, and it is in figure, and filter out irrelevant ones, white. Oh, figure 2. Understand this on 2 running examples of scene setting. Figure 2. Let's go figure 2. So copying and selective copying. So input is blue, yellow, orange, green, red, green, some white and some black, perfectly solved by LTI. Convolutional models that do not need to look at the actual inputs, and output is some white box with a diagonal, and then we have the same order. Selective copying is so we put some white box inside the input sequence and we get the same result. So selective copying can understand those white box are redundant or some bullshit and removes them. And the standard version of the copying test involves constant spacing between input and output elements and is easily solved by time variant models such as linear recurrence and global convolution. Right top, the selective copying task has random spacing. So random spacing puts and requires time varying models that can selectively remember or ignore input depending on their content. Right bottom. Right bottom is about the induction heads. The induction head task is an example of associative. So Harry Potter is about the induction heads. Now that requires retrieving an answer based on context, a key ability of LLM for LLMs. And they have 2 algorithms that does the shit. Very interesting. Where is it? Selective copying. There's content aware reasoning. Okay, to be able to memorize the relevant tokens colored. So it should memorize the relevant tokens colored and filter out the irrelevant ones, white. And the induction head task is a well-known mechanism hypothesized to the majority of in-context learning of LLM. It requires context-aware reasoning to know produce the correct output and the appropriate context. So can you give an example of selective copying in a sentence? Task selective copy only the words that are noun from the following sentence. The cat quickly jumped over the tall fence and chased the bird. Input sequence is this. Selection condition only the nouns cat, fence, bird. The model processes the input elements and applies the selection. Now, this example highlights content-aware reasoning. The model must understand the grammatical role of each word to decide whether it meets the selection. That's very good. In the context of the Mamba paper, is achieved through input-dependent parameterization, allowing the model to focus on relevant tokens dynamic. And can you give an example of induction heads? Why is it called induction head? Associative recall. Sequence and applying them later in context. Concrete example, the next word in the sequence based on prior occurrence. Patterns. Alice likes ice cream. Bob likes chocolate. Alex likes ice cream. All right. So it can reason. So it associates Alice to ice cream. Uh, Challenge for models in that are challenging because the pattern like remembered across potential long contexts. Model must generalize the association even when the input sequence is extended over. Select this task because they use input independent dynamic. Remember and retrieve relevant pattern. The paper demonstrated Mamba perfectly for sequence during training. So even this memory is works on test data even for longer sequences than this is for 4,000x longer than its training length. Wow, that is fantastic, right? And then I want to say, why is it called induction head? Originate from the field of mechanistic interpretability of large languages. It is specifically referred to attention heads in Dresden. Model from inductive reasoning. So it's about that inductive reasoning and attention heads. All right, let's go. Inductive reasoning, attention heads. So LTI models are stupid in selective copying and induction heads. Review their constant dynamics. Not let them select the correct information from the or affect the hidden state passed along the signal and input upon the way. Convolution. It is known that global convolutions can copying them because it only requires time awareness. From the convolutional view, it is known that global convolutions can solve the vanilla copying task but not the selective copying task because it only requires time awareness, but that they have difficulty with selective copying tasks because of lack of content awareness. More concretely, the spacing between inputs to outputs is varying and cannot be modeled by static convolution kernels. In summary, the efficiency versus effect. What about efficacy? Efficiency effectiveness trade-off of sequence models is characterized by how well they compress their state. Okay. So attention mechanisms do not compress and therefore they are not efficient, but they are effective. Efficient models like Mamba have a small state, while effective models have large state that can have all necessary information from. In turn, we propose a fundamental principle for building sequence selectivity, or the context variability to focus on or filter into a sequential state. In particular, selection mechanism controls how information propagates or interacts along the sequence. So it is input dependent. What is section 3.5? Properties of selection mechanism. All right, this is the core of the paper actually, and we are going to deep dive into it. Improving a system with selection incorporating selection into is by letting their parameters that affect interaction along the sequence, the recurrent dynamic are be input dependent. One way, one method. Are there other methods? But I think GPUs are so good, like computing parallel or whatever it is, that people say, fuck it, let it be O of n squared. We are doing it. Algorithm 1 and 2 illustrate the main selection mechanism that we use. What is algorithm? Okay. The main difference is simply making several parameters delta BC functions of the input along with the associated change to tensor shapes throughout. Associated changes to tensor shapes throughout. In particular, we highlight that these parameters have a length dimension L, meaning that model has changed from time invariant to time varying. Shape annotations. So input dependent time varying discloses the equivalence to convolutions with implication for its efficiency discussed next. We specifically choose SB of x linear n of x, SC of x linear n of x, S delta of x broadcast D linear 1 of x, and T delta soft plus where linear D. What is linear D? Linear D, parameterized projection to dimension D. Linear N is a projection to dimension N, parameterized projection to dimension D. So SB of x, SB of x is projecting x to dimension N. SC of x is the projection to dimension N, another one. S delta of x is the projection to we first project x to dimension 1 means constant, and then broadcast d. What does broadcast d mean? I don't know. And tau delta soft plus, the choice of s delta tau delta is due to connection to RNN gating mechanism explained in section 3.5. What is broadcast? What is D an operation that replicates or extends a smaller dimension 1 vector to match a higher dimension target shape along a specific D. So it takes dimension 1 to, so we project x to dimension 1 and then we broadcast it to dimension D. Where in the context of input a scalar x, we replicate into a vector all x. Alright. Shape of parameters are input over we apply this. So you have input sequence with D channels, scalar lower dimension. So broadcasting ensures that this is scalar over. To match the shape of the sequence, it can be applied across all the channels. Example, working parameter is defined. Exactly. Example delta, the time step or gate parameter in this. So delta, by the way, what is delta? Time step or gate parameter in SSM. Here, Y is branch shaping compatibility, efficiency, flexibility, both BLD, batch size, L, sequence length, number of channels. So these number of channels, batch size, if delta is initially scalar, shape 1, applying bracket, vector of shape BLD, ensuring compatible. What is delta? Learnable gating parameter. So even delta is learnable and gating parameter in the selective statement. key component in controlling the dynamic of the model, determination how information is processed and propagated through time, time step scaling, how the state space model evolves at each time step, it modulates state transition in the evolves at each time. So delta governs at each time step how the state space model evolves. It modulates the state transition. It adjusts the speed or scale of how information flow across the sequence. Gate for selectivity. Delta is a gating mechanism. So it is gate for time steps. Gate for select. It's a gating mechanism that which part of the input signals are emphasized or suppressed at different times. This enables the model to dynamically focus on relevant portion of the sequence, improving its long-range dependencies. Input dependent. Traditional linear time invariant models like delta are fixed. Mambo makes delta dependent on the input. This flexibility allows. But it was S delta. The paper described as being derived through a. Okay. No, it was S delta of x. What is SB of x and S delta of x? And what is its name? Sub plus. Alright. Function of delta in state space dynamic plays a direct role in the evolution of hidden state, where delta influences the matrix A and B, dynamically adjusts how the previous state significance. Okay, influence the matrix A and B. Flexibility allows the model to adapt its behavior then improve generalization, moving the fixed time invariant better cross variant selecting. So how does delta changes? Actually, I can reply to, right? What is the mathematical relation of delta and B? So it's computed as so ax of t is delta dot wa plus ba, bx of t is delta wb plus db, and a is sigma delta scaling. The paper doesn't explicitly specify the exact delta to axt, but a typical relation is such axt where wa in learnable weights, BA learnable bias terms, delta gain, sigma delta dot wa. Sigma delta is a nonlinear activation function. We're seeing an activation allowing delta to control the what is the difference? Maybe if we go to the algorithm, we learn this stuff. S and what distinct quantities and the roles in model differ the time step parameter. So delta is a time step parameter or input dependent gating. Let's say this one is derived from the input No, this is not the form. Scaling factor. S delta scaled or processed version. Ah, so S delta is a scaled or processed version. It's a mathematics term. All right, what is soft plus? Oh, the smooth differentiable activation function. Oh, log of 1 plus e to the x. All right, so it's a sigmoid. The choice of S delta and T delta is due to, so you chose S delta to be broadcast D of linear 1 of x and tau delta to be soft plus. Connection to RNN gating mechanism execution explained in this. So let's go over the algorithm. Algorithm 1, SSM S4, and algorithm 2 is adding the selection to it, S6. So algorithm 1 is S4, which is LTI, and adding selectiveness makes it S6. Two up. One for induction head, one for selective copying. So X is Y BLD, Y is BLD, A is parameters to dimension D and N, represent structure N times N matrix, Dn rather than Bn, C is Dn, delta, tau delta of the parameters, softmax, goes to delta, and we discretize delta and A and B, so A and B give parameters. A and B and delta give the discrete version. I see. We had an F delta function. Okay, Fa of delta and A was A bar, and B bar was Fb of delta and A. So delta shows itself in A bar and B bar. That's why ChatGPT can sometimes give you wrong answers. You need to be smart enough. You don't need to be very smart, to be honest. You need to just be smart enough. Okay, so exactly. A bar is Fa of delta and A, Fb of delta and A and B. So B bar is also influenced by A and B, and A bar is Exp of delta A, B bar is something delta A and delta B involved. And delta is a matrix. So A is Rn. What is the dimension of delta? So I don't know. Alright, so delta affects A bar and B bar, and Y is SSM of A bar, B bar, Cx, time invariant, recurrence or convolution, and return Y. Now let's do SSM 4 plus selection, which will be S6. We have X, BLD, Y, BLD, A, Dn, and N times N matrix, the same thing. Now we are using SB of X to give us B, and SC of X, we are making these matrices dependent of X, which is time variant. Instead of using the parameters to give us B and C, we are using input stream to create B and C, and delta is also soft plus of parameter plus is delta of X. It used to be delta c delta of parameters, now it is plus s delta of x, and a bar b bar the same discretization this time, and y is the same SSM. That's it. That was not very huge. Some minor changes made it. Is it the thing that we had, the graph we had? Selection mechanism. So yes, it goes to B, delta, and C, and then it shows itself in Y. Alright, that's very interesting. Alright, that was in the photo as well. So we added a selection mechanism. But what was the P of X again? The P of X is linear n in X, and SC of X linear n in X, S delta of X is but there is no B or C, but just SP of X instead of parameters. Parameter same as X? Let's ask ChatGPT. In algorithm 2, what is parameter? What is its difference from X? Parameter refer to learnable weights and biases of the model. Variable that the model adjusts during training to minimize the noise cycle, which is a W space equation. We had the state space equation WA and WB. I didn't see them. Where is this thing? More gating parameter. Fixed during inference once trained. Constant. Okay, parameters are constant and based on the training data, but X is the input when you wanna use the application. On this parameter, but it is not algorithm 1 versus 2, is an SSM versus a time varying one, not a attention mechanism versus the Mamba. Alright, let's go further. Hardware-friendly primitives such as convolutions, hierarchy, and attention enjoy widespread application. Here we aim to make this efficient on modern hardware GPUs. So it's a conciliation or reconciliation of SSMs with GPUs. Chain mechanism is quite natural, and really works attempt to incorporate a special letting delta vary over time in regard to SSM. As previously mentioned, a core limitation in the usage of SSM is that computational efficiency was YS4 and all derivative use LTR, most commonly in the form of global. So efficient implementation of selective, this is about, and 3.4 is a simplified SSM architecture. 3.5 is properties of selection mechanism. I think that's the important section because it has a photo. And 36 additional model details. Let's go efficient implementation of selective SSM. So we are focused on selective, and then it says about efficient implement. I don't care about it as long as it is applied. Motivation of prior models. That's not super important to us. Okay. Recurrent models such as SSM always balance a trade-off between expressivity. I want to say expressive titty, but it is expressivity and speed. Expressive titty and titties. Expressivity. At least we should say expressivity and speed. As discussed in section 3.1, models with larger hidden state dimension should be more effective but slower attention models, but we want to maximize hidden state dimension without paying speed and memory cost. Now, the recurrent model is more flexible than convolution mode. The recurrent model is more flexible than the convolution model since the latter is derived from expanding a former. So recurrent model mode is more flexible than the convolution mode. Flexible. Recurrent has R, so it is more R flexible than the convolution mode. Since the latter, convolution is derived from expanding the former. Expanding the recurrent becomes, so I think recurrent has a feedback formulation into it, but convolution has like expansion model. However, this would require computing and materializing the latent state H with shape BLDN, which is much larger by a factor of n, and the SSM state dimension than the input X and output Y of shape BLD. Thus, the more efficient mode was introduced, which could bypass the state computing. So recurrent one has an n extra n dimension to it. Even though it is more flexible, it is less efficient. State computation. So that was one of the reasons. Prior LTY more efficient convolution. Prior LTI state space model leveraged the dual recurrent convolutional forms to increase the effective state dimension by a factor of n, 10 to 100. Much larger than traditional RNN without efficiency penalties. Dual recurrent convolutional form to increase the effective state dimension by a factor of n, 10 to 100, much larger than traditional. RNN are not efficient, so the efficiency. So RNN traditional ones without efficiency penalties. They're not efficient. They're flexible. We want to make them efficient. We need to put some penalties for non-efficiency. This section also, these sections are not super important. Section 3.5 is the most important one. Laissez-moi voir. Ah, dude. I'm so happy I slept enough last night. I'm not trading my sleep with anything else in this world anymore. That's it. It doesn't work fine with my system. I have to get my complete sleep. Then I'm a normal human being. And probably even then I need a nap in the afternoon. I need some walking, to be honest. So selective scan, these are prior mechanism is designed to overcome the limitation of LTI model. At the same time, we are going to revisit the computational problems of SSM. We address these with three classical techniques: kernel fusion. So what is the computational problem? SSM didn't have computational problem. It was linear and fast, efficient. This is a kernel fusion, parallel scan, and recomputation. Two main observations: the naive recurrent computation user BLDN, which had a big N, flops, uses flops. What is flops? While the convolutional computation uses OFBLD log L. What is log L? Flops. Convolutional was faster. I thought it was BLD. And the former has a lower former constant factor, thus for long sequence. Okay, even the constant factor matters. These all bullshit computational. These are bullshit. In real life, constant also matters. Thus, for long sequences and not too large state dimension, and for long sequences. Okay, what is long? L and too large state dimension, and the recurrent mode can actually use fewer flops. So L is the length of the sequence for sure. B is, what is B? What is what is flops? What is B is batch size. What is L? L was the length, and what is D? D was number of channels, and what is N? What does channel mean? Hidden states. N is the dimension of hidden state. Floating point operation per second. Floating point operation per second. Floating point operation. Float operation per second. Common measure of computational complexity or efficiency in machine learning and high performance. Log refer to the total number of floating point operations required in the algorithm. Makes sense? B batch size, L sequence length, dimensionality of the input, D is the dimensionality of the input. No, D is the number of the channel. Size, well, we broadcast it to. What is hidden state size? D is the dimension of channel. D is yes, and which is the number of features per time step in the input. Okay, number of features per time step in the input sequence. Explanation of the each time step or token in input is represented as a vector of size t, where d is the number of examples in an IP. D could represent embedding size of a word or token. In audio processing, D could represent number of sequence or channel again. In time series data could represent audio. Why is D called channel dimension? The channel dimension of from its common usage in convolution neural network. How D fits into OLDN. The size of each time step in the input side, the computation causes the example, if your input sequence is an audio sequence L, 64. Okay. What is channel? Channel refers to dimensionality of the features at each time step in the input sequence. Sounds right. This concept we consider with its usage in sequence models and other neural network architecture. Definition of channel in Mamba. Each time token in the input sequence represents a vector of features and a channel. The size of this vector for any feature the channel dimension D is 128. Input to the Mamba model is tensor shape BLD. Channel in different contexts. Audio processing. Interpretation can vary based on the type of data being processed. Natural language processing. Channel represents the embedding dimension of each token. Right? For instance, if each word is embedding 512 dimension space. Audio processing is on frequency bands. 64. Time series data 10. Role of channel in Mama. Alright. Suppose you're processing text data. Input a batch of sentences. Sequence length 50 word per sentence. Channel 300 dimensional word embedding. The input tensor would have a shape of this. Batch size, in this case, alright. I'm going to learn. While in flops, using pure, the two challenges are the sequential nature of recurrence and the large memory usage rather than ladder. Large memory use just the convolutional. We can attempt to the full state H. H is for recurrence. Main idea is to make the material more efficient levels of memory. Channels of matrix are bounded by memory boundaries. So most operation except matrix multiplication are bounded by memory bandwidths. It's interesting to know, common knowledge. Then use our scan operation and we use kernel fusion to reduce the amount of memory I/O. To a standard implementation. Concretely, instead of preparing the scan input of size BLDN in GPU HBM high bandwidth memory, we load the SSM parameters delta ABC directly from slow HBM to fastest RAM, form the discretize and recurrence in the scan, and then write the final output of size back to HBM. This part is part of the memory that I missed. For the sequential recurrence, we observe this one not being linear. It can also be parameterized with the work efficient parallel scanners. We must also avoid saving intermediate state which are necessary for back propagation. We carefully apply the classic technique of recomputation to reduce the memory requirements. Intermediate state are not stored, but in the backward path or input are loaded by the result of few selectors has the same memory. Flash attention. So it is something about memory stuff that they are doing that I don't completely understand. Fused kernel and are in effectivity, the full selective as illustrated there. So this motherfucker, so this orange one are in GPU with RAM and the green ones are in slow HBM. HBM is a slow. That's what it was saying. It's about how they run it on a hardware level. What's section 3.3 about? Yeah, SSM, how to simplified SSM architecture. This is a very short section. I don't want to look at the time. Can you please not pay attention here? Can I put something? Looking at time, taking your time, wasting your time, minutes and hours and seconds wasted my time. Ugh. This is done. Fuck. Don't wash your wallet. Well, what could I do? I vomited on it, so it was the only option. All right. Perfect. Everything is ruined now. Let me keep this half. So now I cannot look at the time. Perfect. All right, what is this section? Simplified SSM architecture. Why should we care about the simplified? So structured SSM, selective SSM, standalone sequence transformation, flexibly incorporated into neural networks. The H3 architecture is the basis for the most well-known SSM architecture, which are generally comprised of a block inspired by linear attention interleaved with an MLP. Comprised of a block inspired, they are comprised of a block inspired by linear attention interleaved with an MLP, multi-layer perceptor block. So it has an MLP. It said we don't need even. We simplified this architecture by combining these two components into one, which is stacked homogeneously. Figure 3. Okay, let's go figure 3. So we have SSM in H3 and an MLP gated, which is added to gated MLP, which I don't know what it is, to be honest. And then we stack them. All right, I can see the stacking to Mamba. Linear projection and square is a rectangle is a linear projection. Input comes, linear project, convolution, and then you SSM it, and then maybe whatever, and then you get it the output. What is this trapezoid? It's again, no, those trapezoids are the MLPs, right? Sequence transform. What is the sequence transform? Oh, okay, it's like a function on it. And Cross is a nonlinearity, activation or multiplication. Multiplication, I think, because activation is sigma. And then we do it convolution, multi-layer perceptron, convoluted, do a sigmoid on it, do SSM on it, and another MLP. Our simplified block design combines the H3 block, which is the basis for most SSM architecture, with the ubiquitous MLP block of modern neural network instead of interleaving these two blocks with. What does interleaving mean? What does interleaving mean? What does interleaving mean? The contents of attention interleaving means alternating or combining layers of. Okay. Let's say alternating and combining with layers of multi-layer perceptron in a neuron. Definition: interleaving refers to arranging different types of layers in sequential order within an architecture. Purpose is allows model or strengths of both. Combination. That's it. So obviously it is interleaved, and compared to H3 block, one more the first model gate with an action function. We block Mamba adds an SSM to main branch. For sigma we use Silu swish activation. Alright. This is inspired by the gated attention unit, which this architecture involves expanding the model dimension D. Oh, D is the model dimension. By control expansion vector E for each block, no software parameters. 3D squared are in the linear projections. 2D for output projection, while the inner system contributes less the number of projections for or much in comparison with this block. We repeat this block interleave with the standard normalization and residual connections to form the Mamba architecture. So it is a layered version of this block. Now let's fix E to 2 in our experiment and use 2 stack of the block to match the 12 2D square transformer in the MHA. Multi-attention, use the so these are more implementation details. Properties, section 3.5. Actually, the 3.4 was the important one, as it had the figure. Now we are gonna go section 3.5. so it's not, first of all, it's not as important, and then it is properties of selection mechanism. Oh, they have one theorem as well. Interesting. Which I'm not going to even mention in my presentation. So section 3.5 will be easier actually. And they have parametrization of delta. That's it. They have some graphs to show. DNA modeling. I like curves. I like them curves and how they wearing off of you. Speed and memory benchmark. Speed. Memory benchmark. Speed. I think they are just lying about it. They go their home and they say. I think it is like They say speed, but they say, oh no, didn't say it like you. Perchance. Speed and memory benchmark. Pretty damn good. Ah, I think you're done. You made it. It was not very difficult. I'm turning to a monster. I can present any paper, just give me 2 hours. Honestly, the papers we do are much harder. Even like economics paper, put them aside, they are very difficult. Then you come to this IR, they have database work, and they have an algorithm. Understanding those are even harder than this paper. It just says, all right, we did this. And they put some photos. Pictures, photos, not pictures. Alright, let's finish it. Properties of selection mechanism. The selection mechanism is a broader concept that can be applied in different ways, such as to more traditional RNN or CNN, to different parameters using different transformations. So S of X is just transformation of X. Oh, gating mechanism is delta. I want to know about it. So gating is about the discretization of continuous time system is well established. Zero order hold which had fa of delta and a f b of delta a and b. We put it in a gauge proof that a theme more broadly delta in SSM can be seen to play generalized roles of the RN and I work on the new and is a principal foundation of heuristic gating mechanism. Theorem 1. When n is 1, a is minus 1, b is 1, s delta of x, linear of x, tau delta cephalus, then the selective SSM recurrence takes the form gt is sigma of linear of xt, ht. What is gt? 1, okay, minus gt ht minus 1 gt xt. In section 0, our specific choice of SL is from this connection where you know that if we go and input xt should be ignored. Necessary in synthetic task, all D channels should ignore it, and so we project the input down to 1 dimension before repeating broadcasting that. Interpretation of selection and elaborate 3 particular mechanisms. So selection mechanism makes it time varied. variable spacing, copying always filtering out relevant noise. Does that may occur between a bit of interest? Is it copying that? Delivery this may validate the model particular for discrete data, but then depends on language fillers. Over the arrays because the model can mechanically filter at any particular input exposure. So this is for audio, right? It's in filtering context. How about text though? It has been empirically observed that many sequence models do not improve with longer context. Despite the principle that more context should lead to strictly better performance, an explanation is that many sequence models cannot effectively ignore irrelevant context when necessary. That's very interesting. An intuitive example are global convolutions, and then on the other hand, can simply reset their state at any time to remove extraneous history. Is this performance extraneous? What is the difference between extraneous and extra? And their performance proves monotonicity with context, like boundary resetting. Are stretched together. Independent sequences tissue can keep them separate by instantiating particular attention. But will blend information between these independent ones, so reset their state at boundaries. Naturally, because boundaries. These settings may occur artificially, packing document together to improve hardware naturally, episode boundary. Or non-effects of interpretation of delta, that's important. In general, delta controls the balance between how much to focus or ignore in the current input xt. That's beautiful. It generalizes RNN gates mechanically. A large delta resets the state H and focuses on the current input X, while a small persists the state and ignore the current input. It's all about the attention and focus. It's crazy. What a paper, by the way. I mean, I don't know how good Mamba works. Large delta says this. We don't have any OpenAI that works with Mamba, does he? A large delta says this. Put on the current input X, while a small delta ignores the. So we are getting more and more information, smaller time. So we want to keep this state such a ignore. Big delta ignore small delta. Whereas a continuous system time step delta. Okay, delta is a time step. So when you make it short, it means that we wanna understand this state more. So it's focused. We make it delta big, fuck that. I don't care. I wanna ignore some stuff. Induction is larger than the system. Focusing longer. Small delta is a transient input that is ignored. Why? It's just completely the opposite of what I said. Okay, I didn't understand this part. My understanding was completely opposite. I thought it's short. Small delta means focus, persistent state, and ignore the current persistent state and ignore the input, while large delta means get the input, forget about the states, and focuses on the current input. There isn't the system focusing on the current input, for longer selecting it and for getting the current state. So there is a balance between input and the state. We remark that while the A parameter could also be selective, it will ultimately affect the model only through its iteration with delta via A bar equals x with delta. The selectivity in delta is enough to ensure selectivity in A bar and B bar, the main source of improvement. We hypothesize that making A selective in addition would have similar performance and leave it out for simplicity. Interpretation of B and C as a sense again, the most important part of this irrelevant here. Models concept can become effective efficiency. In an SSM modeling B and C, B selective allows finger grain control over whether to let input xt into the state or the state into the output one. Can be interpreted allowing the model to modulate the recurrent data. Context hidden state. Content is input, context is the hidden state. Wow. What a beautiful choice of word. Content is input, context is hidden state. Additional model details. Real versus complex. How much time? 3.6. Ooh, we still have 10 minutes. That's the benefits of not looking at time. When you don't look at time, time does not pass. Woo! Additional, I brought time in my control. I want the next 10 minutes to pass like it is 1 hour, and I will make it. Actually, we are done. Even if it spends in 5 minutes, we are done with section 3.6. Wait a second, how long was our 2 hours 37 minutes? We are gonna make it 47 minutes. Additional model details, real versus complex. Use complex numbers. So prior ones we were using complex number, which is complicated, so we just use real, and we are real, which is necessary for strong performance on many tasks in perceptual modalities. However, it has been empirically observed that completely real valued SSMs seem to work well. Dude, extra math is bullshit. We just need simple math, natural number. Make it natural, make it 0 to 10 and we are good. And possibly even better. In some settings, we use real values as the default. Oh, well, for all but one of our tasks, we have decided that is related to the continuous discrete spectrum in data modalities, where complex numbers are output for continuous. Alright, so it says, but not discrete. For real ones, for discrete tasks like DNA, real. For continuous tasks, like audio and video, complex ones are better. Ooh, initialization. Okay. Most prior SSM suggests a special initialization, particularly in the complex valued case. They built the system, the whole Mamba. It's amazing. I don't know how good it is though. Can we use Mamba? Let's check it out. Mamba. App. Is it an app? Your new dates are here. Mamba is dating app? No, okay. Mamba. What is it called? It's not LLM. Okay. How can I use Mamba? How can I use Mamba? Do they have a platform like ChatGPT? ChatGPT. Platform or chatbot like ChatGPT instead is machine learning model or designed for sequence. To use Mamba, you would typically implement it in a programming environment like Python and integrate it to your workflow for tasks such as language modeling, audio processing, series analysis. This is how you can use it. Accessing the Mamba code. The author have provided open source code on GitHub. The code repository includes implementation, pre-trained models, and check the paper or its associated GitHub repository. Requirements for using programming knowledge with Python and machine learning is PyTorch or TensorFlow. Hardware. You need hardware, GPU, for efficient training and inference. Dataset, sequence, data relevant. Install dependencies, and then it also gave us how to run it. Alright. So if it is not ChatGPT, why are we reading it? So this initialization is too empirical. I don't understand it. The finance. Parameterization of delta. We define our selective adjustment as S delta of x with this, which was motivated by the mechanics of. So we observe. Can be generalized from dimension 1 to a larger dimension r. We said this to be a small fraction of d, which is an negligible in the block. We additionally know that the block has an operation that is as another linear projection. So let's do projection pattern of 1 and 0. So this projection is triangle. This is the low rank projection. Yeah. To total thermal uniform following the parameters. For brevity, in our experimental result, we sometimes approve selective SSM as S6 model because they. Alright, empirical DNA sequencing, language model pre-training, scaling laws, and zero-shot downstream evaluation. Alright, I told you, I have even 5 minutes now. Getting a Massachusetts ID saves you time, guys. Okay, you cannot see it. It has information. All the bartenders and bouncers know it. 4.1. We test Mamba ability to solve the two synthetic tasks motivated in section 3.1, then evaluate on the 3 domains each value the autoregressive running. Language model pre-training, scaling laws, and zero-shot downstream evaluation. DNA sequence pre-training and fine-tuning on a long sequence classification task. Audio waveform pre-training and the quality of autoregressively generated clip shows Mamba's computational in post-training and synthesis. What does perplexity mean? Let's read this section too. Selective copying and appendix. The copying is one of the most data. Task. Oh, it was the many previous work with architecture dating direction and no model with data dependent and solved related tasks or defined and defined insufficient criteria. It does not vary use of architecture dating is not an instance of selection mechanism. One confirms that gated architecture such as HCM Table 1 confirms that gated architectures such as H3 and Mamba only partially improve performance, while the selection mechanism S4 to 6 easily solve this task, particularly when combined with this powerful architecture. Induction heads, which was the associated induction reasoning attention head, is a simple task from mechanistic interpretability that is surprisingly vertical in its learning ability of a learner model to perform associative recall and copy, for example. So, Harry Potter datasets. Okay, this is for the language model, right? Synthetic task. Alright, the model on the induction head has a sequence with a vocab size of 16, which is language sequence model for established for an induction head layer which allows variable 2 shows the model precise selective system layer has perfectly related selectively the relevant token while ignoring everything else and it realizes perfect million lexicons or another than saw during training or no. That's amazing. No other goes beyond 2x. It goes 4,000 times x better, but the other method only 2x better. Position of encoding or Jesus. Oh, okay. It's two. Language modeling, really, Mamba architecture and standard language modeling is other architecture on both brain and zero model size to merge GPT. Oh, we set the model sizes, depths, and weights to mirror GPT-3 specification. We use that's interesting, pile data set and follow the training recipe describing Brown method and the scaling laws for as well as the strongest transformer recipe we know is transformer plus lava architectures with the against other recent subquadratic architecture. All in appendix here shows scaling laws under the chinchilla. Is the first attention-free model to match the performance of a very strong transformer recipe. Transformer that has now become standard as the sequence length grow. So it's very impressive. Downstream evaluation. This table is bullshit, I'm not gonna. DNA modeling. Model. synthetic species class. We evaluate models on a downstream task of classifying between 5 different randomly sampling and continuous mouse, pig, hippo, more not llama, mamba. This is the one. Hyena DNA. Gorilla, human, chimpanzee, or audio modeling, long context of the records. These are really good. No free lunch. Pretty models. $7 billion. No free lunch, continuous discrete time. What does ablation means? I need the pronunciation as well. Ablation. Ably. The surgical removal of body tissue. Ablation. Ablation. When there's a machine learning example, it refers to type of experiment where a specific component or feature of a model is systematically removed or modified to assess their contribution to overall. Okay, so the model works this good, and then we remove one part of it and see how well it works. So want to see effect of it. In this process, I help research to understand which part of the model are most important and purpose. All right, I know what it is. I don't want to go further. Ablation, expressivity of delta, the selection mechanism of delta constructed with the projection of input. It even to dimension provides a large increase in performance. It further provides further improvement at the cost of modest increase in parameters, state size, and 16. Perplexity. What does perplexity mean? It is decreasing, so we want low perplexity. What does perplexity mean? Perplexity is a metric commonly used to evaluate language models, particularly in tasks like language or text generation. How well a probabilistic model predicts a sequence of tokens, lower probability, better performance, is 2 to the minus 1 over n sigma 1 over log 2 of pi. So probability of this is the uncertainty of a model when predicting the next token in a sequence formally. Number of tokens, 1 to 1. Alright. So probability, perplexity, lower perplexity means better. Parameters, perplexity. State dimension. Top constant being seen. Oh, we have better. I think there's a some state dimension which can be viewed as a strong action. What is the wording here? strong inductive bias toward continuous time data modalities such as perception signal as is the selection mechanism overcome the weakness. So what is the perplexity of ChatGPT? That's it, paper is done. What is the perplexity of ChatGPT? This is the measure used to validate language model. However, OpenAI has not publicly disclosed the first specific complexity score for ChatGPT model. This lack of information or exact figure for ChatGPT is important to note that while perplexity is a useful measure, it doesn't always the quality of generated complex models. GPT, therefore, even without. Alright, guys, I think we are gonna stop here. Thank you. That was fantastic. 3 hours. We read it. 3 hours.